Warning: this episode contains some controversial statements that might not be suitable for the sensitive viewers, but there are no conspiracy theories. There's only research and it includes a list of scientific sources. Viewer discretion is advised.
Sup guys, welcome to today's show. First off, this is not clickbait. This is not a conspiracy theory. Everything I'm about to tell you in the following 15 minutes, and these might be the most important 15 minutes of your life. Everything I'm about to tell you is 100% backed by research, by the top researchers in the field of cybersecurity in the world. It is doctors and professors at the finest universities all around the world, and I will provide you with a list of sources at the end of this sequence. And then, based on this research, I will draw my own conclusion and ask some rhetorical questions. But the important thing is, at the end of this story that I'm about to tell you, we are gonna prove it or disprove it in code. So we will know for sure, using scientific methods, if this is true or not. Let's commence.
Before the 1970s, all the way back to the time of Caesar, national governments had tried to limit the spread of encryption, trying to keep it a secret. But in the 1960s, though, a family of ciphers by Feistel spread to the public domain, and his ciphers were very secure block ciphers. So in 1972, the US decided to standardize the cipher to be used as a primary encryption scheme for commercial applications all over America and the rest of the world. So why did they do that? Did the US change its earlier stance and decided that it was more important that the citizens had access to secure communications than the need to be able to listen in on their conversations? Had the NSA suddenly become altruistic and grew a conscience? The research community, my dear colleagues, settled on this being the most probable scenario or reason. Is there another reason, though? We'll get back to this question. IBM, together with the NSA, got the assignment to develop the cipher, and in 1977 they published the full specifications of their cipher DES, Data Encryption Standard. And for the next 20 years it was used pretty much everywhere and all over the world. But not inside the US government. They used their own ciphers to encrypt top secret documents and whatnot.
Alright, so this basically works like this. You start with a message. And this message is in clear text. You also have a key. And the key is basically like a password. You need to know the password in order to be able to decrypt the message. So, how does it work? Well, you start by splitting the message in two halves. So you have a left half and you have a right half, often depicted by L and R for left and right. And with the right half, you do two things. First of all, you send it right through in clear text, unencrypted. Secondly, you take a mathematical function called the f function, and you feed this right half into it. And you also feed in the key. So I'm not gonna go into the details here what the f function does, but it does a lot of different encryption related functions using the right half of the message and the key. And what it produces is an output in form of a series of bits. So zeros and ones. And you take those zeros and ones and you feed in the left half. And this is the encryption step. So you encrypt the left half of this message, and you send the right part right through. And now you switch. So on the right here you have the encrypted left half of the message, and on the left you have the unencrypted clear text right portion. And now you do the same thing all over again. And you repeat these steps 16 times. And after 16 times, both of these halves will be equally encrypted.
But not inside the US government. They used their own ciphers to encrypt top secret documents and whatnot. And even though they released the full specification, they never told how they came up with their design choices. Many times researchers asked the IBM and the NSA, why did you choose these S boxes and why did you use this method doing different parts of the encryption? And the answer that they always gave was, because it's secure, trust us. And the algorithm is considered very secure. To this day, no weakness has been found that affects the security of DES more than marginally. But the key size is also very important. The original proposal stated a key size of 128 bits. That means that in order to test all the possible combinations, you need to test 2 to the power of 128 different keys. That is a very large number, approximately the total amount of atoms in the known universe, and it's completely out of reach even to this day with all the computer power in the world. But the death cipher uses 64-bit keys. Allegedly, the NSA convinced IBM to reduce the key size, officially so it could be used in older equipment and cheap hardware as well. But that's not all. If you study the cipher specification, you notice that 8 of the key bits get removed even before the encryption operations begin. So this is actually a 56-bit cipher, not a 64. And if you dig deeper, you realize that the keys that actually encrypt the data never is bigger than 48 bits. However, 48 bits is still tough to crack with a regular CPU. But you can build specialized hardware that can break DES much faster than a regular CPU. Even in the 70s, for large government organizations, even as much as 56 bits were considered within reach in the 1970s, if they had hardware for around $20 million. It's a very large sum even today, and it was a huge sum back in the end of the 1970s. But for a government institution, it's considered pretty cheap if you consider being able to eavesdrop on encrypted information that everyone thought was safe. In 2006, my fellow researchers at the University of Kiel in Germany built the Copacabana. It's a small, low-cost supercomputer based on several parallelized integrated circuits. This low-cost, single-purpose machine was able to crack any DES key in about 7 days, and this marked the definite death of the cipher, which in theory had already been dead since the mid-90s. In the 1990s, the US government realized they unfortunately needed to replace the DES, a cipher which had served them well for the last 20 years, and it's being used all over the world for 20 years. But in the mid-90s, the cyber security scene was vastly different than in the 70s. The encryption research community had grown exponentially, and so had the number of publicly available ciphers. So if they were to release another 64-bit cipher, the world would have picked something else to use. Instead, they might have chosen an even niftier ruse, and that is what this video is really about, but more of this later. In 1997, the US government announced a worldwide competition where researchers as well as regular armchair cryptographers could submit their own ciphers, and the winner would become the new standard instead of DES. Among the 5 finalists were the Mars cipher by IBM, and some other ones by the most famous names in the world of cryptography. Everyone thought IBM would win again, but the prize went to 2 very young Belgian cryptographers that most have never heard of, and their secure block cipher Rijndael. Rijndael standardized as AES, Advanced Encryption Standard, in 2001. With a minimum key length of 128 bits. AES is a very secure cipher with a 3-dimensional inner state and atomic operations that mixes bytes in 3 dimensions. All operations use a mathematical theory called Galois fields, which add to the security, and the key length makes an attack impossible under our lifetime, even with unlimited resources. AES is by far the most used cipher in the world, used in everything from your web browser to your phone, passport, credit cards. No one has found any real weaknesses in AES to this day. So that's it then. The NSA has put a nail in its own coffin by standardizing an unbreakable cipher? Perhaps they got tired of listening to all these mundane conversations while eavesdropping on the world population. Or maybe not. AES is a fast enough cipher in software, but as most ciphers, it is even faster in specialized hardware circuits. For those of you who's seen my assembly school series, you know that an Intel CPU has a couple of basic operations like move for copying data, add and sub for doing plus and minus calculations, CMP for comparing data, etc. And this set of basic operations have not changed very much since the 1980s. However, in the late 2000s, Intel did something that they had never done before. They decided to extend this set of basic operations. They made their own CPU instruction for generating an AES key. This instruction is like a black box. You just tell the CPU and it generates a key for you, and the only one who has any insight in how it's done is Intel themselves and possibly some US government agency. They also added similar CPU instructions for performing the actual encryption and decryption. The rationale behind this is that AES encryption is so common today that it needs to be hardware accelerated. More or less every encryption software today uses these hardware accelerated CPU instructions when creating keys and doing the actual encryption and decryption. This includes applications like Linux DMCrypt, bcrypt, all web browsers, bestcrypt, truecrypt, as well as chat applications that market themselves as end-to-end encrypted. Even if you code your own encryption and you compile the code with optimizations, it will use these hardware accelerated CPU instructions. But what if these new CPU instructions is actually a backdoor, put there in cooperation with the NSA? We must remember the history of the Intel Corporation. It was founded by an intelligence officer who had served the entire World War II as at the predecessor of the CIA. And all this is public knowledge. You can even read it on Wikipedia. And that guy raised all the capital needed to found the company in one single day, almost as if there had been a single investor, perhaps a government agency. And what about the strange name Intel? Is it, as they themselves claimed, an abbreviation for integrated electronics, which is a weird term that too? Or is it an internal joke for the organization's real purpose, i.e., providing intelligence? Well, let's find out. If we were to code an AES implementation that uses these hardware accelerated CPU instructions, and then we code our own software implementation that does not, if we then generate a bunch of keys and we encrypt and decrypt a bunch of random stuff using both methods, and then we compare the two, then we should sooner or later get a different result using the two methods. Or perhaps not. Thus either proving or disproving the thesis that your Intel CPU has been backdoored by the NSA. Let's start coding.
Sup guys, we have a lot of ground to cover, so let's get started with the code right away. I have created a template project based on my bash BS template build system. It's in the repo. I'm just gonna change a few things. It's a pretty empty .c file. It has created 3 files. So a .c file, which is pretty empty. And then we have some includes in the h file. We have some type definitions of different integers. And we have a couple of macros converting between the types. And it's a pretty standard make file as well, just compiles this .c file. One thing though, the C standard is set to C2X by default. If you are running the latest GCC version, which I am, 14 something, you should change this to C23. But otherwise you can use the default C2X, or you can remove this word. And I'm also going to change those macros. So I want this to be 1 byte, 2 byte, 4 byte, 8 byte. So that's how I want to reference those. I also want to create a type definition for a bigger int and a 128-bit integer, because we're going to need it when we create our key schedule. That's, by the way, why I have named this KS, key schedule, and I'm going to describe what that means in a little while. So we're going to use an unsigned bit int 128, and that's going to be our int 128, like so. Let's also create an alias for that. So $16 bytes, I guess it is, will be int 128. And I'm also gonna create a couple of other types. First of all, we need to have a... Alright, so we're gonna define a int 32, which we're gonna call a word. So a word usually depicts a int 16, but in the sense of the AES encryption, they call an int 32 a word. So that's what we're going to use. We are also going to need a int 128, which will be a key, because the keys are 128 in what we are focusing on. There are different variants of the AES cipher, but let us start there. And there are, by the way, there are two things that two routes they could have taken when it comes to backdooring the CPU AES instructions. Either they attack the key schedule, which basically is used to create something called subkeys. And it's the subkeys that actually encrypts the data, but we use the regular key to create those, and that's what we're going to do today. And the other way is the actual encryption and decryption. And this is the most probable thing, I would say, because it's simpler and more effective. But it could be either one. So we will first test the key schedule, and then we'll test the encryption steps. And you take what this program is going to do. It's going to do what AES does. It takes 128-bit key, and it produces 11 subkeys of the same length, so 128. And these are divided in a total of 44 ints, so regular int 32, and that's those words here. So we need to have an array for that. So let's type that as well. Let's say we have, well, it's going to be an array of words. So let's call this word array. 44 of those. So let's see, is it anything else? No. Let's see, let's define the functions we're gonna need. First I'm gonna go and grab the algorithm for the key schedule. I don't know this one by heart. So this is what we are going to follow. And it looks pretty intimidating, but it's not so advanced after all. So in this 44 array we go word for word, and every fourth word uses this formula, and the other three in a row uses this. So first you do this, then you do this 3 times, and then you do this all the way through the whole array. So basically what we're going to do is we're going to figure out the index of the actual word that we're going to change, and we're going to change it by the by an earlier word. So let's say this is the 4th word, then maybe we take the data from the 1st and do something, and then maybe in the 5th we take from the 2nd, and so on and so forth. So here we just grab the right value. Here we also grab the right value, another piece of this word array, and we run it through the G function. And the G function is pretty advanced, so we'll take that last, but I will create a dummy function for that. So it's going to return a word, and it's going to take a word as an input, and also what round we are in. So there are 11 subkeys, so we do 11 rounds of this. And for now I will only return the input W, but later on we will fill this out with real calculations. But that's the last step. Here we just iterate through these and copy some stuff around. And one note, the 4 first of these words is the input key. So the first thing we'll do is take the key. If we'll zero out all of these 44, we will take the input key and put it inside of index 0, 1, 2, and 3. And then we start doing this from the 4th and onwards. So that's how it's going to work. So let's define this G function. It goes from word to word, and we have an int 8 as the round. We're also going to need 2 helper functions, because we need to convert between words which are 32 bits, an integer, and the individual bytes, there's 4 bytes in an int, so we need to grab those 4 bytes in an easy enough kind of way. So let's see. We can call those subwords. We can even define a type for them. So type def, it's going to be of int 8, and they are subwords, or subword, let's say, and there are four of them. Can we do it like this? We cannot return an array like that. I think it will be easier if we just do this and then we use it as a pointer. So we're gonna have one function which takes a word and it produces subwords. So word to subword. So it's gonna return subwords, and it's gonna take a word as an input, so an integer. And then we're gonna have a function for the other way around. So there, the return value will be a word. We're gonna call this subword to word, and we're gonna take subword star. So the vice versa. Okay. What else do we need? Well, we need to have a main function. Let's just define it like this for now. And finally, we need to have the actual function that calculates these subkeys. So let's call that generate keys, and it's gonna return. It's actually gonna return a word array like this, but since we cannot return an array, what we're gonna do instead is just use a word pointer and then allocate as much as we need. So word star as return value, and the input is just a key. No, wait a second. Yes, it's a key like this, right? So let's see, word. This is a word array. No, it's right. Okay, so yeah, that's all we need. And let's start with those small utility functions that just basically takes an integer and splits it up into 4 bytes, and vice versa. So let's see, and if you wonder why I haven't commented these out, I will comment them out, of course, when we are going to compile, but it's harder to read without the colors, so I want to keep them like this as long as I can. Okay, so let's go. We will start with the word to subword. So this will return a subword star, and it's going to take a word W, and we can do this in just a few lines, but I think it's easier to use some intermediate variables. It's easier not to make mistakes. So let's create some int 8, a, b, c, and d, which will be our output variables. And we're also gonna need a subword pointer. And in hexadecimal, an integer of 32-bit looks something like this. So DDCCBBAA. So we want to grab those A's. That's the lowest part of the number, and put inside of the A. And then B to B, C to C, and so on and so forth. Right. Let's see, how did we define subword, by the way? Int 8, yeah, that's right. And how do we grab something? Well, we use some binary bitwise operations. And if you want to know more about how they work, you should watch my episode Binary Operations. I go through it very in depth. So I will not explain every step of this, because I have done so in a couple of videos now, and I want to focus this video on the things that matters for this program. Okay, so let's see. Let's start by grabbing those A's, and we do that by selecting them using a so-called mask. So we want to create a mask that has zeros where we're not interested in the data, and we have F's where we are. So as you can see, we have the same number of numbers here, and those 6 are zeros, which means we are not interested in the D's or the C's or the B's. We are only interested in the A's. And since these zeros are at the beginning of the number, we can reduce them to just this. Which means that A will be equal to the word that we take as an input, and we do an AND operation against that mask, and now we have our A. Simple enough. But it's a little bit trickier when we do the B's though, because if we fill in those zeros again, this time we want those 2, so we remove those zeros and we put zeros right here. So far everything is okay, but when we do this AND operation, the result is going to be we have the zeros here, and then we have the, let me just see, and then we get our B's, and then we get 2 zeros at the end. And zeros on the right side matters. So this will be reduced to this. So we need to take care of those 2 zeros and push the B's to the right. So it'll be like this. We take the W, the word, and we run it against this mask. So now we have this, and now we need to push them 8 bits to the right, because 2 digits 2 hexadecimal digits is 8 bits total. So if we push those to the right, we will end up with just the bits. And we can do the same technique with the other ones. So we just keep adding zeros here, and this will be 16 bits that we're gonna push. And in order to get the D, we do the same, but we have the FF 000000, and we push this 24 bits. So if I have calculated this correctly, now we should have our values inside of here. So now we simply need to return them in some way, and let's make a malloc allocation. So let's start by defining a size, and size is going to be equal to well, we can simply just do size of a subword times 4. So our P will be equal to a subword casted malloc of size, and we need to cast this to an integer because the size is an int16 here. And we can assert that we have a P. And let's zero out our P. And then we should copy this stuff. So let's see how we easiest do that. Let's create another pointer. Let's call one of them ret. So ret will be equal to this, and we'll assert ret and 0 ret. And then we point P towards ret, and the first position should hold the A. So we'll set this equal to A, but we will also increase P afterwards, because then we can just do like this, and we don't need to increase after we have put the last one there. And now we can simply return our ret, and we have our utility function. We also need one to go the other direction, and that's actually a bit simpler since we don't need to allocate and stuff. We can just return a word. So let's see, this is subword to word. It's going to return a word, and it's going to take a subword SW. We are going to assert that we have a subword. And if you don't know what assert is, it basically checks this condition. And if it's true, nothing happens. If it's false, it exits the program with an error message. So it's quite simple to use in applications like this in order to handle the error cases. Okay, so let's see. What is the easiest way to achieve this? Let's see. Maybe we can have a word pointer. And yeah, if we just point this towards the subword, we need to cast this thing to a word star. I think the memory is in the right order for it to just work like this. Well, I guess we'll see, won't we? So in that case, we can just return star p like this, I guess. If they are in the right order, which they are probably not, by the way. How did we put them there? First we put A, so A is at index 0, and we need it, let's see. Are they? Let's try it out and see what happens. So let's say we have a word W and we have subword SW. Right, so let's see. We take let's say we have a word that we set to A, B, C, D. And then we set our subword equal to word to subword, and we give it the word. And I'm not going to check for any errors now. I'm just going to print something from it. So let's say we print hexadecimal values of 2 of them. So let's see, HHX is for printing 1 byte. And then we do the same again. We have percent O2 HHX, and O2 is the number of digits we want to have. And what do we want to print? We want to print, let's say, the first subword and the last subword. We need to cast them as, maybe we don't. And let's be good and free our subword allocation. Like so. Let's see if this compiles. I forgot to comment out those things. Where did we put them? Here. this is in the H file, line 26. Where is this here? Line 26. Oh, 36. Those numbers, right, this should be a subword, nothing else. Int main conflicting types, that is also true. Don't need any arguments. And compile. Will it work though? Let's see. Yes. Get the first and the second. And let's see. Are they in the order we want? So this is the first in the array. Yeah, I guess we can work with that. Just need to match it on the other end. So let's see. If we try to go back then, if we have word 2, and before we free this thing, we say word 2 is equal to subword to word, and we give it the subword. And then we print this thing, and this should be, well, a regular X with 8 digits. And this is word 2. Yes, we get, oh no. Here we begin with the A. And we had the other way around, right? No, we begin with the A. Okay. So then everything works. We have successfully created the first functions. All that is left, well, that's quite a lot, but the next thing we would want to do is to create this generate keys kind of thing, and then after that we will create the G. But I think this is enough for one episode. I really hope you liked this episode, a very special one. Please like and subscribe, and we will see each other very soon. Thanks for watching. Thanks for tonight.